Okay, Calc 4, Lecture 20, Linear Algebra and General Vector Spaces, Coordinates, and Basis. But I will discuss basis, basically, in this section. So, let's say that, again, another definition. S, say U1 up to UN as a subset of V is a basis for V if 1, V is span of S, 2, S is linearly independent. S is linearly independent. Okay, so let's look at some basis for, say, some spaces that we know, like Rn's, and then we discuss basis for, say, solution set of a system of equations, for example. So let me erase this. Well, I have to emphasize these two are kind of, sometimes you just need to prove one of them. You will see in different situations. But you have to prove both of them. This might be easier than this one, but they're related. So this one is like you set up a system of equations and then show that that system of equations has only zero solution. But this one you have to set it equal to some vector and show that it is consistent. So this one is harder, but this one is easier. So let me give you some examples of in order. So for R2, basis for R2 is what? R2 is the span of these two vectors, 1, 0 and 0, 1. Sometimes you know them as E1 and E2 in physics. They know them as I and J. And these two vectors are in fact x and y. This is E1 or I, and this is E2 or J. Okay, so the ij in physics, in fact, that set ij is a basis for R2. And you can write any vector as a linear combination of these two. It's very simple. So if I have a vector, say, x and y, just any vector, that is x times the first one plus y times the second one, right? So any vector is a linear combination of these two, and these two are linearly independent. Remember what I said, the ones are at different positions. Everything is zero except one of them, which is 1, and the ones are at different positions. So this is generated by these two. These two are called standard basis. So standard basis for R2 are in fact I and J. Now for R3, you can guess that they are in fact I, J, and K. So let me write down I, J, and K here for you. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is span of E1, E2, E3, or IJK. I, J, and K. Again, you can see this is like those examples I gave you. The ones are at, everything is zero except one of them, and these ones are at different positions. So these vectors are in fact linearly independent. And you know from physics that you can write any vector as a linear combination of these three, and this is the E1 or I, this one is E2 or J, and this one in the Z direction is E3 or K. Okay, so E1, I, J, K. And any vector can be written as a linear combination of these three. Let me write just a generic vector, x, y, z is x E1 plus y E2 plus z E3. Just check. Okay. Okay, so, oh, I forgot the 3 here. So this is by R3. So, this subset of R3 is basis for R3, and this is a basis for R3. And for Rn, you can guess that Rn is span of EIs. Rn is span of E1, E2, En, and EI is in fact so what is EI? EI is all zeros, 0, 0, dot, 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 and there is a 1 in position I. So this is the ith row. So EI is like this, and as you see, EJ has 1 in jth row. So each one of them has a 1 in a different row. So they are linearly independent. It's not that hard to show, and any vector in Rn can be written as a linear combination of them. So any vector in Rn, say x equals x1 up to xn, is in fact a sigma I from 1 to n xi ei. You can check easily that this is the case. So we can say that this set is a basis for Rn. Now, Rn in fact has infinitely many bases, any R, R2. R2 has infinitely many. So, basis is not unique, but this is called standard basis. So, that is called standard basis, and let me show you basis for say R2 other than E1, E2. Let me erase this and say that example. Say take this S to be these two vectors, say 1, 0, and the other one let it be 1, 1. Let's see, this is this linearly independent, so let's say K1, 1, 0, plus K2, 1, 1, equal to 0, 0. So this will give me K1 plus K2 is 0. The second one is in fact just K2 equal to 0. And you will get that K1 is also 0. So linearly independent. So this tells me that this is linearly independent. Next is to see if they span R2. So I have to put on the right side a generic vector in R2. So this is any vector in R2, right? So let's see if what happens if I do this. So I have k1 plus k2 is x, and the second one is k2 is y. So this gives me k2 equals y. So if I put k2 here, it gives me k1 is x minus 1. Okay? So, yeah, it is, because I could find k1 and k2, it is consistent, and I can find k1 and k2, so I say that R2 is spanned by linearly independent, spans R2. Spans R2. So this set is linearly independent, it spans R2, and therefore it is a basis for R2. So then let me erase this thing. So S is a basis for R2. Okay, so let me show you what it looks like in R2. So this is the 0, 1 or 1, 0 here, and the other one is this 1, 1. 1, 0 and 1, 1. Okay? And they span, in fact, they span. We show that they span, like geometrically, well, it's not, I don't know. Now you can geometrically even show that they, in fact, span, but, well, that algebraic is enough. So, now, what is, say, what other, okay, so let me give a basis for, the n 2 by 2. That is span of what? You can guess what I can write here. The standard basis 1, 0, 0, 0, right? Then put 0, put 1 here. Just change the position of 1, 0, 0, 1, 0, and 0, 0, 0, 1. Okay? That is a basis. That is a basis for M2 by 2. Let's say P3. I can say that it is a span of what? Span of 1 as function, polynomial just 1. Polynomial just x. Polynomial just x squared, and polynomial just x3. You can see that easily. That is A0, A1, A2, A3 times each one of them, and so any polynomial can be written as a linear combination of these, and they are linearly independent. How could you show that they are linearly independent? One way is to use the Wronskian, in fact. You can show that the Wronskian of these is not 0. Well, it's instructive to show that this is linearly independent using Wronskian. In 2 ways, I show that this is the Wronskian. So what is the Wronskian of these functions? 1, x, x squared, and x3. Say x. In fact, these are as functions. Let's say. So okay. Okay. Anyways, at x. So it is determinant of this. So let me write the determinant notation. And that is 1 x, x squared, x3. Derivative is 1 and 2x, 3x3, x2, 0, 0, 2, 6x, and the last one is 0, 0, 0, and just 6. Oops. Right? Isn't this beautiful? This is an upper triangular matrix, right? An upper triangular matrix has determinant equal to the product of this. So it is 1 times 1 times 2 times 6, which is 12. It is not 0. So these vectors are linearly independent. So S equals 1 x, x squared, and x3 is linearly independent. independent. And also they expand P3. They expand P3. How? Oh, that one is obvious. If I have Px, A0 plus A1x plus A2x2 plus A3x3, right? So that's it. So this is in the span of this. So Px belongs to the span of 1, this is 1 here, 1, x, x squared, and x3. It is a linear combination of those vectors. So this guy here is a basis for P3. And you can see it has 4 vectors. We will see that P3 has dimension 4, in fact, not 3, although it is P3, but it has dimension 4. So let me I said that a basis for, so let me erase this. And we will, when it comes to differential equations, we will see that we talk about the space of solutions, and that space has a basis, and so this will come up in differential equations part of the course. So another example is, let me go back to say that system of equations that I wrote. I can't remember the coefficients. Let me just write some coefficients for you. Plus 3x, let's say x3 minus 25x4 is 0. Then it is x2 minus 5x3 minus 12x4 is 0, something like that. So this one and this one are R and S, let's say, and so x1 will be minus 13R plus 25S, x2 will be 5R plus 12S, and x3 is R, x4 is S. So this is in fact written in this format, and you should get used to writing them like this, and R times minus 13, 5, 1, 0, plus S, 25, 12, 0, 1. Okay, so the solution space, now I can say space because I know this is space. So solution space is the span of these vectors, those two. Minus 13, 5, minus 13, 5, 1, 0, comma, 25, 12, 0, 1. So let me erase this and this too. Span of this. But look at this, these two vectors. These two vectors are, if I draw a line here, you can see that it includes 0, 1 and 1, 0, right? I don't care what happens above this. And I have 2. So these 2 are in fact linearly independent. This is like E1, this is like E2. So at a certain point, below a certain point, the vector looks like some EI. Okay, they all look like some EI. Usually it is E1, E2, E0 to some point. So these are linearly independent. So we can say that this set S minus 13, 5, 1, 0, comma, 25, 12, 0, 1 is a basis for the solution space. So what you find, or what you have found in some problems that I gave you, or the problem in the exam, for example, then that was in fact you have found the basis for solution space. Okay, so let me stop and continue next time. Okay, see you next time.